Let's listen to Anima Anandkumar, a director for research in machine learning of NVIDIA. Let's see what she has to say on the problem.
Welcome. This is literally the holy grail for AI. If you think about us as humans, we have such impressive abilities. We can learn from very few or no data points. This is called few-shot or zero-shot generalization. For instance, a child which has never seen the dolphin, seeing it for the first time, will still know it is an aquatic being. It's a living thing. It can swim. It has eyes. All these are abilities that are still far for AI to achieve. Similarly, humans can overcome all kinds of corruptions to our input perception. For instance, all these noise is part of the popular dataset called ImageNet-C, and it's still very challenging for the current AI methods to do well on such corrupted data, especially when that is not seen during training. If you only train on clean images, how well can AI generalize to corrupted images is still an open question. And this is really critical for so many applications such as autonomous driving, where we cannot foresee all possible perturbations and scenarios that an AI may encounter. Another impressive ability of us as human beings is the ability to create new things, new art, new music, and that comes through compositionality. We're able to grasp concepts. What does it mean to have different kinds of musical notes, different genres, and then from that compose an entirely new piece of music. Such compositionality is still far from what we can achieve in AI. Currently, most AI merely interpolates, meaning it looks at training data distribution and can do interpolation within that distribution. But compositionality asks for entirely new samples to be formed through composing different concepts together and doing that in a creative way. And this is another aspect we want to study carefully in our AI methods. And as I said, all the inspiration comes from us, and in fact from infants, which can do such impressive learning that's yet to be realized with any AI, even to a minute extent. For instance, infants do unsupervised learning and grasp all these representations around us, and only get supervision much later on. And most of supervised learning right now is not based on this concept and in fact expects labels during learning. And hence the aspect of how we can do good disentanglement learning, disentangle different concepts and different variations, and be able to compose new samples, be able to overcome noise and perturbations. These are all aspects that's really critical for us to realize in AI. If you look at where current AI is, this is far from what humans can do. For instance, I'd like to break down any AI algorithm into three parts. How does it deal with data? What kind of data does it rely on? What are the priors it incorporates? And finally, how does it do decision making? What kind of tasks is it trained on? What kind of actions will it make in an environment? And with deep learning, currently it's extremely data heavy. We expect data sets that are massive and require just enormous amounts of human labeling. And with priors, we don't have robust priors. And to me, this hits at the heart of inability to handle corruptions and perturbations. Our priors are weak For instance, just assuming it's a convolutional network is not enough to overcome all these different perturbations. And indeed, there are lots of instances of where AI can be fooled so easily. One popular example is if you're putting some simple blocks in an image and it completely changes what the AI thinks is in an image. And so we should be able to overcome all these kinds of perturbations for AI to be deployed in many real-world situations. And finally, the tasks with which we are designing AI are extremely simplistic. Usually there's a fixed data set with a fixed objective. And many times that's not only limiting but also dangerous. We've seen now so much more awareness these days on the bias in our AI models. For instance, popular face recognition models are extremely biased against women and minorities, especially Black women, and to be used in sensitive applications such as law enforcement is extremely troubling. And hence, it comes to us to ask how we can move away from such simplistic design of benchmarks on biased datasets. And so the next frontier I see in AI is to disrupt each of these facets. When it comes to data, we want to think about unsupervised learning. Mostly go from scratch and decide how to do disentanglement of different variations, learn new concepts, compose and form new samples. I think this is the next frontier for AI, to do unsupervised AI efficiently. When it comes to priors, we want to have much more robust priors. How to do away with just merely feed-forward neural network architectures and encode more domain knowledge. And this is where I'll emphasize how we can derive inspiration from our own biological mechanisms in the brain. And lastly, the task has to be much more adaptive and not encouraging overfitting to a fixed data set. And I'll show you some interesting new challenges we have formed where all the current AI fails pretty badly, but humans can do it so effortlessly. And this opens up the question of how we can design better methods that can handle multiple tasks, that can do lifelong learning efficiently. So let's start again with drawing inspiration from our own biological mechanisms. How is the brain able to handle all these kinds of perturbations and noise? How can it do perception so well? So here we draw lessons from neuroscientists, and I'll show you a few very clever experiments they've done. I got this information thanks to Doris Sau, who's my colleague at Caltech and a neuroscientist, and collaborating with her has really opened me up to so many amazing things that our brains can do. So let's see some of those examples. So the brain, unlike a standard neural network, has feedback connections. A standard neural network in the artificial realm just merely has feed-forward connections. Whereas in the brain, as we are taking input from the external world, it goes through various layers. It goes through the layers of visual cortex and ultimately IT cortex. But then after that, there is also the period of feedback where you get feedback all the way from IT cortex back to the visual cortex. And an important study in neuroscience is to ask, what is this role of feedback? And in some of the experiments that have been done, it's shown that this feedback process is essential for our perception. Many times, subjects don't even see images if this feedback process is masked. So if you do an intervention and don't allow for feedback, there is no perception, which is very interesting. And more interestingly, feedback seems essential for figure ground segregation, or what we call in computer vision segmentation. So here the green dot we know should be separate from the background, right? And to do this process of segmentation in the brain, feedback appears to be critical. And that's why it takes us longer to perceive images with these objects compared to just the plain background. And lastly, in another experiment, it was shown that removing feedback also makes us human beings extremely brittle in our perception. For instance, in this paper, they did an experiment where they asked the human subjects to quickly recognize what's in an image. And in this case, as high as 67% of the participants wrongly classified the image. So when you're asking them to make quick decisions, they're not able to use feedback mechanism in their brains. And hence this shows that humans are also brittle when you remove feedback from their perception. And lastly, there are theories suggesting that feedback may be essential for consciousness. So this global neuronal workspace theory states that information only becomes conscious once it reaches all the way to frontal lobe and ignites, so to say. And by then, it's accessible to the rest of the brain through the feedback pathways. So unless you make this information available through feedback to a large parts of the brain, it looks like we cannot have consciousness. Given that feedback is so core to our perception and intelligence, how can we build that into our AI models? That's what I'd like to show next. And indeed, feedback is not just in neuroscience, it's in so many other fields. For instance, in control theory, it's well known that closed loop control, where we have the feedback, is vastly superior to open loop control, where there is no such feedback. In fact, for an unstable system, closed loop is essential to stabilize it. You just cannot achieve stabilization in an open loop manner. And that shows that stabilization requires feedback. And similarly, we also believe in the brain that feedback can stabilize various processes. And this gives us another motivation to use feedback in AI. So perhaps the simplest model to incorporate feedback in learning method is known as predictive coding. So it does use the concept similar as in control theory, where you correct with the error signal and progressively improve the predictive estimator. This is biologically more plausible because it does not require backpropagation. But on the other hand, if we are using such mechanisms to update the weights in an artificial neural network, this is extremely inefficient, and previous works haven't shown this working even at the MNIST scale. Right? So given that it's extremely hard to train networks with mechanisms such as predictive coding, our focus will be different. We don't want to replace backpropagation for training our networks. Instead, we want to use these kind of predictive coding mechanisms with feedback to help overcome corrupted examples. And that's what we'll see. So this work is known as neural networks with recurrent feedback, generative feedback in particular. And this recently got accepted to NeurIPS, which we are very happy about. And this is thanks to a collaboration between Caltech and NVIDIA, also collaboration between neuroscientists such as Doris Tsao and machine learning researchers and computer vision researchers. So this is really great to see multiple areas of expertise come together. In this work, what we did was to ask how to build a principal feedback mechanism into any standard neural network, such as the convolutional neural network. So if you recall the convolutional neural network, it takes the input image and then runs it through a series of operations. Now that could be convolution, rectified linear units or ReLU, the pooling, and then finally the prediction. So what we now ask is, can we reverse this set of processes to now have a feedback So essentially what the feedback does is try to invert this neural network. And that's the feedback mechanism. But the thing is, this network is not inherently invertible. In standard networks are not. But the idea is by trying to see how to invert well, we can regularize and overcome corruptions effectively. So this is the actual operation of feedback where we change what the ReLU and max pooling units do based on what the feedback G is telling. So you're now changing the feed-forward process in the next iteration based on the feedback. So that's the broad intuition behind this feedback mechanism, that we will now modulate or change the feed-forward process based on the feedback answers or feedback signals. So given this feedback mechanism, we can now jointly train this CNNF both on classification loss, so that is the cross-entropy loss, you want to fit it to the target label, and then the reconstruction loss. So you also want to reconstruct the input image or some intermediate feature as well. So if the input image is a clean image, then that reconstruction makes a lot of sense. If it's a corrupted image, you want to reconstruct the clean counterpart of this image. And hence, we can now incorporate both jointly the maximization of prediction accuracy, but also minimizing the reconstruction error in reconstructing these features. And hence, this has properties of both predictive requirements as well as some generative requirements. So if you look at how it does on MNIST, because we can easily visualize this, we can see that initially these are clean images, but we add corruptions at test time. So it's never seen this during training. It's only seeing the corrupted images at test time. It can still overcome and denoise this. That's because it's learned how to reconstruct clean images, and even if you give the corrupted images only at test time, it's able to project it back to the manifold of clean images. And this is a capability that's not present in standard feed-forward neural networks. And with this, we can see much better robustness to adversarial samples, even with standard training. So that is, at training time, the network has never seen any adversarial or perturbed samples. And so what you can see is that this feedback mechanism can overcome adversarial samples even with fairly large amount of noise to a much greater extent compared to the standard feed-forward network. And also, interestingly, this CNNF model needs more iterations to handle harder images or higher levels of noise. This is also in line with biological experiments where it takes more time to perceive a more complex or a harder image compared to an easier one. And hence, by changing the noise levels, we can easily look at how much of feedback is needed to overcome these perturbations. And we also see that if you combine the CNNF with adversarial training, that is, now you're showing these adversarial samples during training time, it can now do best of both the worlds, both good clean accuracy and good adversarial robustness. For instance, you can see it's beating the standard neural network on both clean and adversarial accuracy. And the important thing to note here is that clean accuracy, you don't need feedback, right? So if you're just operating on standard clean images, feedback doesn't appear to give any benefits. On the other hand, feedback is really useful if you're now handling with perturbed images, because you can get now help by projecting it back to the clean manifold with the feedback. And that's how we can get really good adversarial accuracy by doing one iteration of feedback in this plot. And so this design of CNNF is based on the principle of self-consistency, right? And this also aligns with the theory in our brain that we have an internal generative model and we want our perception to be consistent with that model. So if we are seeing some external input, we always query this generative model and look at whether it's consistent. And that's where feedback plays a role. And so we can design this as a mechanism that takes any input image, even a blurred out or perturbed input image, tries to overcome those nuisances, nuisances like the blur or lighting and other kinds of nuisance, and then overcomes those nuisances and perceives it to be a cat. Right? So there's some kind of denoising mechanism happening with this feedback. And so we can formally state it as an equilibrium point where the most likely label for the sample is consistent with the most likely reconstruction of the features given the label. And another crucial additional aspect here is the Z, which is the latent variables or the nuisances. And this captures the fact that standard feed-forward neural networks are not invertible. So you need latent variables to attempt to invert and reconstruct lower-level features from higher-level features. So you can incorporate all of this into designing such a self-consistency rule. And essentially what our feed-forward and feedback iterations do is try to reach to this equilibrium point. And so there's also a nice connection to generative classifier in the way we design our feedback mechanism. So going all the way back to a standard logistic regression. So what it does is attempt to classify a set of samples using a linear separator. By itself, it does not have any awareness of the generative distribution. That is, in other words, we have no idea what P of X is where X is the input. All we attempt to do here is to classify the labels. So this is the standard classification framework. On the other hand, we can impose a certain generative model and do Bayesian inference under that model. And that's known as a generative classifier. And so the counterpart of a generative model for logistic regression turns out to be the mixture of Gaussians. So that means if the input is indeed a mixture of Gaussians, then Bayesian inference in this turns out to be the same as logistic regression. So we can attempt to do the same in a neural network. We can ask, is there a valid generative model that is a distribution P of X and Y, a joint distribution of X and Y together? And if you now take this joint distribution and do Bayes rule, that is, come up with the conditional distribution of the label given the input, does it correspond to a CNN? So any architecture I begin with, can I reverse engineer through a generative classifier? And what would be such a generative model? So we call that generative model deconvolutional generative model. And what it does is it tries to invert these layers of the neural network. And that's what is the feedback mechanism. So the feedback mechanism, because of the non-invertibility, also has to have these latent variables. And so you can imagine these latent variables to capture all kinds of nuisances and variations, which is lost in the feed-forward process. Because the feed-forward process tries to remove these nuisances and get to a classification or a prediction. And the feedback tries to reverse engineer and build back these nuisances to construct these lower layer features. And so that's the intuition behind capturing both feed-forward and feedback mechanisms in the same model. So given any standard convolutional neural network, we can reverse engineer and propose a generative model that we call the deconvolutional generative model. And if you do Bayes rule in this deconvolutional generative model, you recover the feed-forward prediction from the convolutional network. And so that's great that this is now a principled way to build feedback as opposed to some arbitrary feedback in a feed-forward network. And this also aligns well with the Bayesian brain theory, where it's hypothesized that brain also does Bayesian inference. So we have this internal generative model, and we take the external input and some form of Bayesian inference is happening in order to come up with predictions and perception in our brain. And so it's great that we can now come up with this principled approach to add a generative feedback into any given feed-forward neural network. And so this is just an informal theorem saying that indeed, if you construct the deconvolutional generative model in this way, and you do classification according to that generative model, you recover back the CNN. And there's some details. I'll ask you to refer to the paper for that. And so now we can get the architecture of CNN with feedback, or the CNNF architecture, by enforcing self-consistency and doing iterative inference in this deconvolutional generative model. So we can first start with the standard feed-forward mechanism. Then we do the feedback mechanism. And in both these cases, we are also doing inference on these variables Z, which are the latent variables, or you could interpret them as the nuisance variables. And so this is unsupervised learning, because we don't have access to latent variables during learning. This is now for adding unsupervised learning to standard supervised learning, which is also very interesting. So you can do this alternatingly between feed-forward and feedback mechanisms. So just unrolling the same loop here, we recover our CNNF architecture. So as you can see, there is a lot of thoughtful, principled approach that has gone into designing this architecture. And the idea is, once we do the feed-forward loop, we can do a feedback loop, and all the time we are also updating our estimates of latent variables, and we can do this over several iterations. And hence we are both now changing our predictions with each cycle, and also changing our reconstruction of the lower layer features. And doing this jointly can now make this network far more robust than just the standard feed-forward mechanism. And just to kind of remind you that architecture again, as you can see, this feedback mechanism is able to now update the answers or the outputs from the feed-forward mechanisms, especially units such as rectified linear unit and max pooling unit, now take information from the feedback units, and hence over time you get updated results. So to summarize this part of the talk, what I showed is, first of all, biological inspirations for robustness. So neuroscience experiments have shown that our brain has recurrent feedback, and that is so essential for us to have robust perception. It's so essential for us to do segmentation. It's even potentially crucial for consciousness. So given this, we then go about building feedback into any standard neural network architecture using the Bayesian principles. So we ask, what is a valid generative model? And if you do such that if you do Bayesian inference in this model, you recover the given feed-forward architecture. And that is the deconvolutional generative model. And with this, we also see the role of unsupervised learning, even for predictive tasks such as classification. So here, as you can see, these latent variables capture the nuisances that are not labeled. And these nuisances are essential for us to be able to reconstruct lower layers from higher layers. And so we believe this architecture will have many other use cases in addition to robustness. We've just barely scratched the surface here. So when it comes to few-shot learning, uncertainty quantification, lifelong learning, I believe feedback will play a crucial role. And indeed, we've drawn inspirations from other areas such as control theory, where feedback mechanism is essential for stabilization, and we'll pursue how to connect that with neuroscience and machine learning. Now, in the next part of the talk, I'll give you an overview of our recent work that will appear at NeurIPS, where we designed a new challenge known as Bongard Logo to test human-level concept learning and reasoning. Compositionality is at the core of human intelligence, and this is another aspect we'd like to test carefully in our AI methods. And so we got inspired by the Bongard problems. So this was created in the 60s more as a way to have puzzles for us to solve. The idea is there are a set of 6 positive examples, so that is the set A, and 6 negative examples, the set B. And so all these positive examples share a certain concept that the negative examples don't. And so given now a new example, can you classify it into one of the two? So just by staring at these images, you can already intuitively grasp what the potential concepts are. For instance, all the images in set A have 2 like blobs or shapes, whereas in set B it's all one continuous connected body, right? So these are aspects that we humans can grasp very intuitively without even being mathematically sophisticated. And so the question is, can we now have AI methods solve such puzzles? But then we hit a roadblock if we try to directly use this Bongard challenge. It has only a few hundred examples, and all our deep learning methods are data hungry. So we don't want that to be a constraint, because we want these AI methods to learn well. But once they've learned, we want to make sure they haven't just memorized and they're able to do compositional understanding and do well on these few short examples. So for that, we went about creating Bongard Logo, a challenge based on programmatic generation. So we'll see that Logo is a visual programming tool, so it helps us create these images well and do it at scale in an automated way. And the other thing was we created 3 kinds of shapes, so the free-form basic shapes and abstract shapes. So the idea is, by creating this diversity of shapes, we also want to make sure that the AI methods can do well on these different kinds of challenges. For instance, the free-form shape is just, as you can see, free-form. Basic shapes involves different polygons. And then the last one, the abstract shape, is explicitly about compositionality, because we are now creating more complex shapes based on simple shapes. And so in all these cases, we've now turned it into a few-shot binary classification problem. So it's few-shot because all we are given is 6 positive and 6 negative examples. And then you have to answer whether the test instance, whether it's a positive or a negative example. Because there are only 6 training examples for positive and negative class, this cannot overfit on the training data, right? But on the other hand, these different problem instances, about 12,000 such problem instances, all have related underlying concepts, right? They share underlying concepts together. And hence, this few-shot learning can benefit from understanding the underlying concepts. So that's why we argue that this benchmark can test for how good the AI methods do concept learning and compositionality compared to standard computer vision benchmarks. So we wanted to have some core concepts of human cognition when we designed this benchmark. So one important concept is known as context-dependent perception. We humans can change the concept based on the surrounding context. But for most of the standard pattern recognition AI methods, this is not possible, because they try to memorize what different patterns look like and then classify them. So as you can see in this example here, the same object, because if you try to relate it to the other objects here and look at what is the common property, the property is having 4 straight lines. Whereas here in these set of examples here, the common property is 6 straight lines. So this way the concept is not fixed to a shape. It can change depending on the context. And so that we can capture well in our Bongard logo challenge. Another important aspect of human cognition is analogy making and compositionality, right? So we can compose simple shapes to build more complex concepts. And we can do that explicitly here. You see these small circles all come together to create this bigger abstract shape. And that's why we created this abstract test set or abstract set of problem instances with few-shot learning. So that's the second one. The third one is having infinite vocabulary. Like I showed you in the example in the beginning of the talk, a child can look at dolphin at the first time and still know that it's an aquatic being. It's not limited by a finite vocabulary, right? So it can continue to learn new concepts. And similarly, we want in this challenge to continue to create new kinds of shapes and geometric arrangements. It's not limited to just a finite set of categories. And again, an AI should truly be good at concept learning. Otherwise, it cannot cheat and do well when you have an infinite vocabulary. So we believe all these 3 properties of having the concept be context dependent, having the analogy making compositionality aspect, and finally having infinite vocabulary makes our Bongard challenge truly a good test of human level learning and cognition. So now moving on, I wanted to just quickly give you an overview of the logo language that helps us do this procedural generation. So the good thing is now we have a program associated with every image, so we can now use this also in our AI methods potentially. And the other benefit is with this we still retain human interpretability. So remember, we want humans to do well on this challenge, and then we can test the AI methods. And so what we see is all the state-of-the-art meta-learning methods that just use the images in this challenge do quite poorly compared to humans. Both the human experts and the amateurs do pretty well on this challenge, but you can see that different meta-learning methods do the best on different kinds of challenges. Whether free form, it's one method, the basic shapes, it's another method, and so on. And so this shows that there is not uniformly a best method for meta-learning on this challenge. The other aspect then this motivates us to ask is, we humans have symbolic reasoning as well in our brains. There's a lot of evidence that we store certain concepts in our brain. So can we do the same and design neurosymbolic systems? And that's what we did. And we added supervision from the action program, and then we trained an LSTM to decode and predict what the underlying action program is. So using this in addition to image features now gives us much better interpretability of the underlying concepts. So the hope is if the AI method can decode the actions more accurately, then it should be helpful in this Bongard logo challenge. And that's what we see in our results, that having this program synthesis, so essentially now having a neurosymbolic approach, gives us the best results across the board. There is still a gap from human level performance, but it's still better than all the other AI methods. So this tells us that the future will be neurosymbolic methods in many settings that require few-shot learning, that require extrapolation, that require robustness. And so Summarizing this Bongard logo challenge helps us scale the traditional Bongard challenge to now essentially infinite set of program instances, and each problem instance is a few short binary classification problem. And I also gave you the thought process we went through when we designed this challenge, that we wanted human-like cognition that involves the concept being flexible and context dependent. We wanted to capture the compositionality and the analogy making property of human cognition, so simple shapes can create more complex ones. And finally, we wanted an infinite vocabulary that humans can do very well with, but the current AI methods cannot. And we see that across the board, neurosymbolic methods do the best compared to just merely neural methods for this few short learning problem. In this talk, I gave you some key ingredients of human intelligence: feedback, compositionality, and causality. Feedback is an essential mechanism in our brain. It enables robust perception. It even is postulated to enable consciousness. Taking inspiration from the Bayesian brain theory that our brain does Bayesian inference, we aim to construct a generative model into any given neural network. And through this principled approach, we could now build feedback into any given neural network. And hence, we now achieve inherent robustness to a much greater extent than standard neural networks. In the second part of the talk, I gave you an overview of the Bongard logo challenge. This is a new benchmark for testing human-level compositionality and reasoning. What we did was construct a few short learning instances. So each problem instance has 6 positive and 6 negative examples. And so any standard method that overfits on data will not do well here. What we saw was the neurosymbolic approach holds the best promise for achieving good performance on such a benchmark. And thus, we have 3 key ingredients from human intelligence: feedback, compositionality, and causality. And by building this into AI, we are closer to our dream of realizing human-level intelligence. Thank you so much.